The fourth test flight of Starship gave space fans some of the most breathtaking footage ever, with both stages of Starship landing controlled on the ocean, intact. What a tough guy. Worth noting that the ship would have failed on re-entry if made of aluminum or carbon fiber, as they can't take the heat. Yes, Musk made the right call in choosing the materials for the ship. Today, let's explore the strength of the material chosen to build Starship. SpaceX has long recognized the crucial role of material strength in their missions. In mid-2020, Musk revealed they would develop a proprietary stainless steel material called 30X. Recently, he called it SX300 and announced on X that they will further hone it to withstand even higher temperatures. This move seems directly related to the change in the heat shield cooling mechanism that Musk mentioned on X recently. Accordingly, they switched to a passive glass heat shield over almost the entire area, instead of actively cooled steel, to reduce weight. Exciting, right? The latter refers to transpiration cooling, a fascinating method that not many people discuss on YouTube. Very interesting, but we might talk about it in future videos. SpaceX has been building Starship with stainless steel from early on, but initially they planned to use carbon fiber composite. The community was abuzz when, in the fall of 2018, Elon announced switching from carbon fiber to stainless steel, even after successfully building and testing a massive 12-meter diameter carbon fiber tank. Everyone assumed the grand Starship would be made from carbon fiber. Even his own team was surprised by this decision, and Musk had to convince them strongly. We've all seen it. The fourth test flight has proven that abandoning expensive carbon fiber for stainless steel was one of the best decisions SpaceX has ever made, if not the best. You saw how the flap took heavy damage from the heat during re-entry in Flight 4. The plasma toasted it to pieces, yet the booster still managed a soft landing. Actually, right after the fourth test flight, Musk revealed that he himself was surprised the flap lasted so long. The back of the flap had no heat shield, just bare steel, and incredibly, the steel held up despite the extreme heating. Don't even imagine carbon composite in that scenario. The ship wouldn't have fared well at all. Yes, I'm talking about its heat resistance. Let's make a simple comparison. Stainless steel can withstand temperatures of up to 800 degrees C, while carbon doesn't melt, but the resin in carbon fiber composite does, and it can only withstand up to 200 degrees C. The temperature Starship endures during re-entry can reach up to 1,500 degrees C. These numbers also answer an initial hot debate. Stainless steel is heavier than carbon composite. The reality is, if you use composite carbon fiber, you need a heat shield, if not a complex and bulky thermal protection system to protect the ship. With stainless steel, the TPS can be designed simpler, lighter, and quicker. So paradoxically, stainless steel lightens the load. Oh, and if you've noticed, in Flight 4, SpaceX seems to have deliberately left a few spots without heat shield tiles on the Starship, at least 2. These spots are at the aft section, not strategic locations, and seem fine if they get a bit damaged, so I believe this isn't accidental. They spend months installing and checking the heat shield tiles, so this action seems to test the material's resistance when launched without heat shields. Trust me, if it were made of carbon composite, they wouldn't dare do that. But it's not just about the material enduring high temperatures. The super cold liquid oxygen that SpaceX puts inside these thin-walled tanks is as cold as minus 207 degrees Celsius, while the outside of those tanks can reach several hundred degrees Celsius during ascent. Re-entry? The surrounding temperature is 1,500 degrees C, hotter than hell itself. So the issue is, not only must the material withstand high heat, but it also needs to endure a wide temperature range, from extremely cold to extremely hot, without deforming and ensuring the structural integrity of Starship. When exposed to the extreme elements of space, this is a real plus, and could be the difference between life and death. We've talked about the exceptional high temperature resistance of stainless steel, but the real reason Elon Musk chose it is its durability over a wide temperature range. Most steels are very brittle at extremely low temperatures, but not stainless steel with high chrome nickel content. That actually increases in strength, and the ductility is still very high, at temperatures around minus 330 degrees Fahrenheit. Stainless steel retains a ductility of 12 to 18%, which is very high compared to most other types of steel. Very ductile, very tough, no fracture issue. From prototype SN8, SpaceX switched from stainless steel 301 to 304L stainless steel. Both are stainless steel, but this is a significant switch. 304L also has high chromium and nickel content. Chromium and nickel provide good corrosion resistance, hence it is one of the most commonly used steels in the world. 301 is used for springs and coils. 304 has higher chromium and less carbon, making it more corrosion resistant, which is why it's used for kitchen equipment and pots. The L in 304L stainless steel stands for even lower carbon content, while regular 304 can have up to 0.08% carbon. 304L can have up to 0.03%. Remember, Starship is made of welded steel rings, so the weakest point will always be the welds. While 301 welds are slightly stronger at higher temperature, at cryogenic temperatures, the strength of 304 welds is 4 times stronger. This switch should allow SpaceX to keep the welds of Starship as they are when finished, without any complicated, expensive, or even impossible aftertreatment. So it's no wonder his team was convinced. It's vastly superior, right? You want to undertake the biggest mission. You need to pay attention to the most basic things, the ones that form the foundation of your weapon. Since then, they have taken material durability very seriously. It's not out of the question that some rings on Starship and the booster on the next flight will use this new material, along with some heat shield areas using the new thermal protection mechanism. Continuous innovation. Truly amazing. Besides the extraordinary final shape they show us, I really want to sneak into the factory to see exactly what they are using to build new Starship. And we can't overlook a very important reason: cost. You know, SpaceX's motto is cost saving. If you didn't know, carbon composite is very expensive. After cutting the fabric, it is impregnated with a high-strength resin, which is quite complex. Developing advanced carbon fiber structures takes a long time to perfect, with 60 to 120 layers of carbon fiber stacked to create the final structure. Each kilogram of carbon fiber composite costs $135, and with 35% scrap, it effectively approaches $200 a kilogram. Stainless steel, about $3 a kilogram. You want to see how superior Starship's materials are? Oh, it's time to take a look at our neighbor, the Russian Soyuz. Soyuz was developed back in the 1960s, and if I'm not mistaken, it's made from a variety of materials, mainly aluminum alloys. Now it's the 21st century, and I wonder if they've made any improvements to their materials, or if it's a case of, if it works, just let it work. To be blunt, aluminum alloys have a low density, around 2.7 G per cubic centimeter, making them nearly 3 times lighter than stainless steel. However, they conduct heat much better, and they don't withstand high temperatures as well as stainless steel. Additionally, stainless steel has higher tensile strength, meaning it can withstand greater forces without breaking. This increases the load-bearing capacity of the structure or product, so Starship is more reliable for operating under harsh conditions and high loads. Materials with high ultimate tensile strength usually have a longer lifespan due to their resistance to fatigue and damage over time. That's why Starship can be reused, while Soyuz cannot. Soyuz is an old design, and it won't be surprising if Russian scientists are working on improving it with better materials, but they need to move faster. Material strength is an incredibly important science to ensure the structural durability of a product. What do you think about SpaceX's development of the ESX-300 steel alloy? Comment below. I love open debates. Thank you so much for joining us. I appreciate that. Keep looking up, and we'll see you next time.